Ever just, look at something simple, like a glass of water, maybe, or even just the air, and think about what's really going on down there at the tiny level.
Oh, absolutely. It's fascinating. Everything around us, it's all built on how atoms connect, how they're held together.
Right, this invisible architecture.
Yeah.
And understanding those connections, those forces,
Mm,
that's the key to understanding why things behave the way they do.
exactly. It dictates their properties.
And that's our deep dive today. We're going into those fundamental forces, the ones that shape molecules and make them interact. We got some great focus points from you, our listener, especially about molecular shapes and the different kinds of bonds.
Yep, that's the plan.
So we'll tackle that, aiming for those aha moments, you know, without drowning in jargon.
Sounds good. And really, to get started on shape and how molecules interact, we have to begin with polarity. It's foundational.
Okay, polarity. Let's break it down. What is it? What causes it?
Well, polarity happens when you have atoms bonded together, but they have different electronegativity.
Electronegativity.
Yeah.
That's the pull an atom has on electrons in a bond, right? We talked about periodic trends.
Yeah.
It goes up and to the right on the table.
Precisely. Think of it as electron greediness. Some atoms just pull harder on those shared electrons in a bond.
Okay, so some atoms are electron magnets, basically.
That's a great analogy, actually. So when one of these electron-hungry atoms bonds with one that's less hungry, the electrons aren't shared 50-50.
They spend more time near the greedier atom.
Exactly. The more electronegative atom pulls that electron density closer.
Can you give us an example? Make it concrete.
Sure. Take hydrogen chloride, HCl. Chlorine is way more electronegative than hydrogen.
Okay.
So the electrons in that HCl bond, they hang out much closer to the chlorine. Since electrons are negative, this gives the chlorine end a little bit of a negative charge. We call it a partial negative charge, delta minus.
And the hydrogen end.
The hydrogen end, losing out on electron density, gets a little bit positive. A partial positive charge, delta plus. This unequal sharing, that's a polar bond. And the whole HCl molecule ends up with a positive end and a negative end. It's a polar molecule.
Got it. So unequal pole leads to uneven sharing, which leads to these partial charges. Is there a way to, measure how unequal it is?
Yes, definitely. We look at the difference in the electron negativity values between the two atoms, and this difference actually helps us classify the bond type.
Oh, interesting. How does that work?
Well, there's kind of a scale. If the difference is really small, say 0 up to about 0.7, the electrons are shared pretty equally. We call that a nonpolar covalent bond.
Like carbon and hydrogen, CH bonds.
Exactly. That difference is only about zero point 0.4, very nonpolar. Now, if the difference is roughly between zero point 0.7 and 1.7, the sharing is noticeably uneven. That's a polar covalent bond.
Like our HCl example.
Yep, HCl's difference is about zero point 0.9, falls right in that range.
And what if the difference is even bigger, over 1.7?
If it's greater than 1.7, generally it's considered an ionic bond. At that point, it's less like sharing and more like one atom completely takes the electron from the other, a transfer.
Okay, that scale makes sense. 0 to zero point 0.7 is nonpolar covalent fair sharing. Zero point 0.7 to 1.7 is polar covalent lopsided sharing. And over 1.7 is ionic, basically a donation.
You got it. And understanding polarity is so crucial because it sets the stage for how molecules interact with each other through what we call intermolecular forces, sometimes called physical bonds.
Right, so we're shifting focus now, not the bonds inside a molecule, but the attractions between different molecules, intermolecular forces. Why are these important?
These intermolecular forces, or IMFs, are the attractions between neighboring molecules. Now remember, they're much, much weaker than the chemical bonds within a molecule.
Weaker, okay.
They're super important for physical properties, things you see every day, like boiling points, melting points, how quickly something evaporates.
How so?
Well, think about boiling. You need energy to pull molecules apart from each other so they can escape into the gas phase. If the intramolecular forces are strong, the molecules are stickier.
So you need more energy, a higher temperature to boil it.
Exactly. Stronger IMFs mean higher boiling points and also lower evaporation rates because it's harder for molecules to break free from the liquid surface.
That makes total sense. So what kinds of these intermolecular forces are there?
We usually focus on three main types, and we can rank them by strength, generally speaking. Strongest are hydrogen bonds. Then come dipole interactions, and the weakest are London dispersion forces.
Okay, let's start in the middle then. Dipole-dipole. What are those?
Dipole interactions happen between polar molecules. Remember HCl. It has that positive end and negative end. That's a dipole.
Right.
So when two polar molecules get close, the positive end of one molecule is attracted to the negative end of its neighbor.
Like tiny magnets attracting each other.
Mm-hmm.
Opposite poles pull together.
Precisely. The more polar the molecule, the bigger those partial charges, the stronger this dipole attraction will be.
So the molecule's own internal polarity dictates this external attraction.
Yep, it's built right in.
Now, hydrogen bonds. You said they're the strongest type of IMF we're discussing. What's special about them?
Hydrogen bonds are like a super strong version of dipole. They happen under specific conditions. You need a hydrogen atom that's bonded directly to one of three very electronegative and also very small atoms. Nitrogen N, oxygen O, or fluorine F.
Hydrogen bonded to N, O, or F.
Got it.
Why those three?
Because N, O, and F are highly electronegative, they pull electron density away from the hydrogen very effectively, creating a large partial positive charge on the H. And they're small, so they have a concentrated partial negative charge themselves.
So it creates a really strong dipole.
A very strong dipole. Take water, HO. Oxygen is very electronegative, bonded to hydrogens. This sets up a strong attraction between the partially positive H of one water molecule and the partially negative O of another nearby water molecule. That's the hydrogen bond.
And water's unique properties, like its high boiling point for its size, surface tension, that's because of these hydrogen bonds.
Absolutely. The extensive network of hydrogen bonds in water is responsible for so many things. High boiling point, high surface tension, its ability to dissolve lots of stuff, even its high specific heat, which is crucial for climate regulation. It takes a lot of energy to break those H bonds and heat water up.
Wow. Okay, so hydrogen bonds are a big deal. Now the last one. London Dispersion Forces, LDFs. Weakest, you said, but present in all molecules, even nonpolar ones.
That's the key thing. LDFs are universal. Every single atom and molecule experiences them.
If there's no permanent dipole, like in a nonpolar molecule.
It comes down to the electrons always being in motion. Just randomly, at any given instant, the electrons in an atom or molecule might not be perfectly evenly distributed.
Like they momentarily bunch up on one side.
Exactly. For just a fleeting moment, you get a temporary, instantaneous dipole. A tiny lopsided charge distribution.
Okay.
And that temporary dipole can then induce a similar temporary dipole in a molecule right next to it. The slightly positive side of the first molecule attracts the electrons in the second one, and vice versa.
Ah, so it's like a chain reaction of temporary dipoles.
Kind of, yeah. Leading to a very weak, very short-lived attraction. These forces are constantly forming and breaking.
But if they're so weak, how important can they be?
Well, individually they're weak, but they add up, especially in bigger molecules. Larger molecules have more electrons overall.
More electrons means more chances for these random fluctuations.
Right, more electrons, bigger electron cloud. It's easier to get these temporary imbalances, making the LDFs stronger overall. That's why large nonpolar molecules like octane and gasoline can be liquids at room temperature. The sum of all those weak LDFs becomes significant. Size matters for LDFs.
Interesting. So even the weakest force can pack a punch if there's enough of it. Okay, let's switch back now to the forces inside the molecule. Intramolecular forces. Chemical bonds.
Right. These are the strong guys, the ones holding atoms together within a molecule. They determine the chemical properties, reactivity, flammability, that sort of thing.
And the main types are?
We'll focus on three: ionic, covalent, and metallic bonds.
Okay, start us off with ionic bonds.
Ionic bonds usually form between a metal and a nonmetal. Remember our electronegativity scale. This happens when the difference is large, typically over 1.7.
So one atom really wants electrons, the other doesn't mind giving them up.
Pretty much. It's an actual transfer of one or more electrons. The metal atom loses electrons, becoming a positive ionication. The nonmetal atom gains those electrons, becoming a negative ion, an anion.
And they do this to get stable, right? Like the noble gases, the octet rule.
Exactly. They're trying to achieve that stable, full outer shell of electrons, usually 8 the octet. Hydrogen aims for 2, the duet rule. So the transfer lets them reach that stable configuration.
And the bond itself is?
The bond is the strong electrostatic attraction between the positive cation and the negative anion. Opposites attract, very strongly in this case.
Like table salt, NaCl. Sodium gives an electron to chlorine.
Perfect example. Sodium becomes Na plus S, chlorine becomes Cl. The strong attraction between them forms the ionic bond, holding the salt crystal together. These ionic compounds are usually hard solids, and they conduct electricity when melted or dissolved because the ions can move.
Okay. And how do we compare how strong different ionic bonds are? Say, comparing NaCl to something else.
We can think about it using the ideas from Coulomb's law. Basically, two main things affect the strength. First, the size of the charges on the ions.
Bigger charges mean stronger attraction.
Yes, higher charges lead to stronger bonds. So something like magnesium oxide, MgO, where you have MeO and O ions. That bond is generally much stronger than in lithium fluoride, which has Li and O ions. Plus 2,2 attraction is stronger than plus 1,1.
Makes sense. What's the other factor?
The distance between the ions, or really the size of the ions. Smaller ions can get closer together.
And closer means stronger attraction.
Right. Inverse relationship. So again, comparing LUF to, say, KBr potassium bromide, Liu and Fo are smaller ions than Co and Bro. So Life usually has a stronger bond because the ions are closer.
But which matters more, charge or size?
Generally, the magnitude of the charge is the more dominant factor. If the charges are different, that usually outweighs the size difference.
Okay, higher charge, stronger bond, smaller ions, stronger bond. Charge usually wins out. Got it. Now, covalent bonds.
Covalent bonds. These happen between two nonmetal atoms. And here, it's about sharing electrons, not transferring them.
Sharing to reach that stable octet again.
Exactly. They share pairs of electrons so that each atom feels like it has a full outer shell. Covalent bonds are generally not as strong as ionic bonds.
And we can split these two based on electronegativity.
Yes, back to our scale. If the difference is between 0.7 and 1.7, it's polar covalent. Unequal sharing, partial charges like HCl. These molecules can often dissolve in water, like dissolves like, and might weakly conduct electricity.
And if the difference is small, below 0.7.
That's nonpolar covalent. Pretty equal sharing, no significant charges, like CH bonds or ClCl in a chlorine molecule. These are often gases, don't dissolve well in water, don't conduct electricity.
You mentioned earlier that shape matters too, even with polar bonds.
Oh, absolutely crucial. Take carbon dioxide co-Euro. The CO bonds are polar, but the molecule is linear symmetrical, OCO. The two bond dipoles point in opposite directions and cancel each other out. So co-Euro as a whole is nonpolar.
Versus water.
Right. Water, HO, also has polar OH bonds, but the molecule is bent, not linear. So the bond dipoles don't cancel, they add up, making the whole water molecule polar. Geometry is key for overall molecular polarity.
Okay, it's a really important point. Bond polarity versus molecular polarity. Well, that's bond type. Metallic bonds.
Metallic bonds, found in pure metals. It's a different kind of model. You have the positively charged metal ions, the kernels, arranged in a lattice structure.
Right.
And the valence electrons aren't stuck to any one atom. They become delocalized. They form a kind of sea of electrons that can move freely throughout the entire metal structure.
A sea of electrons, what does that do?
It explains almost all of the classic properties of metals. That free-moving electron sea is why metals conduct electricity and heat so well. The electrons can easily carry charge or energy. It's also why they're malleable and ductile.
How does it explain malleability, being able to hammer them flat?
Because the layers of positive ions can slide past each other without breaking the overall structure. The electron sea just flows around them, acting like a flexible glue, holding it all together. It also explains their luster, the shininess, how the free electrons interact with light.
Fascinating. So it's like positive ions floating in a shared electron soup. And these bonds are strong.
Generally, yes. Metallic bonds are quite strong, leading to high melting and boiling points for most metals. Often stronger than ionic, which are stronger than covalent, though again, IMFs affect the actual physical state.
Okay. Now, we keep mentioning the octet rule. Can we just quickly summarize its role in all this bonding?
Sure. The octet rule is the driving principle. Atoms want stability, like the noble gases, usually with 8 valence electrons, or 2 for hydrogen helium. It's the why.
And bonding is the how.
Exactly. Ionic bonding achieves it by transferring electrons. One atom loses to get a full inner shell, the other gains to complete its outer shell. Covalent bonding achieves it by sharing electron pairs, so atoms can count shared electrons towards their own octet. It's the fundamental motivation behind forming compounds. There are exceptions, but it's a great starting point.
Understood. And finally, Lewis dot diagrams. How do they fit in? What do they show us?
Lewis diagrams are our way of visualizing this. They're simple sketches. You use dots around an element symbol to represent its valence electrons.
Just the outer shell electrons.
Just the valence electrons, yep. Then, when you draw a molecule, you show how these dots are arranged. For covalent bonds, you show pairs of dots shared between atoms, often drawn as a line for each shared pair.
And for ionic?
For ionic, you show the result of the transfer. The metal ion usually has no dots left, it lost them, shown with its positive charge. The nonmetal ion has a full set of dots, shown with its negative charge, often in brackets.
Do they show anything else important?
Yes. Crucially, they show lone pairs of valence electrons on an atom that are not involved in bonding. These lone pairs take up space and push bonding pairs away, which is really important for figuring out the molecule's actual 3D shape, its geometry.
So Lewis dots give us the electron bookkeeping, who have what, who's sharing, who's not, and clues about the final structure.
Exactly. They map out the valence electron landscape.
Wow. Okay, we've covered a lot of ground, from electronegativity and polarity.
Through the different strengths and types of intermolecular forces, hydrogen bonds, dipole-dipole, London dispersion,
Then into the strong intramolecular bonds, ionic, covalent, metallic.
tying it back to the octet rule and visualizing it with Lewis structures.
It really shows how everything from why water is wet to why metal shines
Yeah.
comes down to these fundamental attractions and repulsions between atoms and molecules.
It's the hidden architecture, like you said at the start. Understanding these forces gives you a powerful lens to see the world.
So a final thought for you, our listener, to take away.
Mm-hmm.
Next time you notice something like oil and water separating or sugar dissolving, but sand not, think about what we discussed. How might polarity and the different types of intermolecular forces explain those everyday observations? Look around and see if you can spot these forces at work.
It's everywhere once you start looking. And, there's always more depth, molecular geometry, VSE pure theory, hybrid orbitals, maybe topics for another deep dive.
Definitely sounds like potential future explorations into this amazing hidden world.